Hello, welcome back. So in my previous presentation we made a start on turning points in calculus, and we're going to continue with that, and we're going to start with this example here. We've been given the task of fencing off a robotic arm, and we need to gain the largest possible area around the arm. We are given 480 metres of fencing, and we're going to make the assumption that the shape of the area is to be four-sided. So for example, a square or a rectangle. So what's the maximum amount of area we could achieve? Would a square give me more area than a rectangle? Let's find out. So what I'm going to do with this is I'm going to just go through the example reasonably quickly because it's fairly straightforward. If you need to go through it again, you can always go back to the beginning of the video and watch it again. But the maths is fairly straightforward, and then I'm going to give some discussion around that, around the aspects of the relevance of it. Okay, so let's have a look. So what we've got here, if you think about it, if we take our fencing as this square here, or rectangle, we've got X and Y, so we'll designate one side as X and one as Y. And what we can get in the extremes is we can have a long, thin rectangle this way, where Y is very, very long. And if you think about it, this distance of X could be as, down to a metre, which wouldn't be much use for the robotic arm, but anyway, just for argument's sake, it could be a metre wide, give you a lot of length this way in the north direction, but not much width. This one's the other extreme, so it could be only a metre this way, or even less maybe, but quite long in the y direction. So it would be handy one way, but not much use really. This one is meant to be a square. I don't know if it is or not, but it's meant to, how precise it is, but it's meant to be a square. You probably, like me, have a sneaky suspicion that will give you the maximum net area. Let's find out. So there's a shape, and if you think about it, we don't expect, we don't know, we'd have to plot it, but we'd expect that the shape would go something like we did previously in the previous example. Let me just get my pen on, where we'd get something like this. Whoops, let's get rid of that, it's awful. Whoops, I wonder if Control Z works on this. It does. Making hard work of this. Okay, back in action. Right, we'll try that again. Let's use a line. So plot a graph. And we suspect, but we don't know, that we'll get something like this kind of shape, where the area, whoops, so like this, where the area is a maximum as we get towards X being in the middle, really a quarter of the overall, we suspect. We'll see. Let's have a look at the maths. So what we're going to have, well, the area is found from X times Y. Very simple. Now that doesn't give us a solution yet of how to solve it, and it's not going to work. We can't differentiate this and get a solution because we've got two variables. We need just the one, the X, because we're going to just use one of them. Obviously Y is dependent on X, but we need to get rid of one of the terms, so we're going to get rid of Y. And how do we do it? Well, another formula we could use is to go with the circumference around the outside, which I'll shorten to Sir, and that would simply be 2x plus 2y. Very straightforward. If you think about it, you've got two of these x's, two of these y's. So whatever shape it was, rectangle, square, that formula would still apply, and that would give you the overall surrounding, the circumference. Okay, so I need to rearrange this so I can substitute in to get rid of this y. So let's have a look at that. So to rearrange this, I would get, let's have a look. Oh, I've also got that this equals 480 meters. Let me just shuffle this over to the left a little bit. Conscious we're running out of space. Okay. So 480 meters. Okay, so if I rearrange that, I would end up with y would equal 480 minus 2x and then that would be divided by 2 and that would be divided by 2. So if you see what I've done there, I've carried the 2x over to the side, it's become a minus, so I've basically subtracted it from both sides, then divided through by the 2 to get y on its own, so I've got this result, and obviously that would tidy up. I'm going to move to the left slightly, so y would tidy up to 240, and that's 480 divided by 2 minus just x. Now if I take that and substitute that into my original formula, I'm going to get this. A would equal x, put it into brackets to start with, 240 minus x. Okay, multiply out the bracket, I'm going to get A would equal 240x minus x squared. Okay, so far so good, nice and easy. Okay, differentiation, I'm just going to shuffle up a little bit here. So changing A over the change in x is going to equal, so 240x differentiated is just 240, then minus 2x. Now when all that is equal to 0, missed a d out there, dx, then obviously 240 must equal 2x for that to all equal 0. So what we're looking at is when, if you remember my previous presentation, if you've not watched it, this might not make too much sense to you, but it's telling us the turning point. So when that shape on our previous graph had a maxima point where the gradient was 0, it's going to give us our x value. Okay, so let's have a look. So 240, so let's do a therefore 240 must equal 2x, so therefore x must equal 240 divided by 2, which very simply is 120. Okay, so then what is the area that's covered when we've got x equal to 120? So basically we've got a square, haven't we, because 120 happens to be a quarter of our 480, so we've got 120 times 120 gives us the area, and 120 squared, easy to do in your calculator, and I'm sure some of you can do it in your head, gives us a total of one, let's put the pen on, let's move it up a bit while we've got it. Right. So that's 1, 4, let's give it a title, area equals 400 meters squared. Okay, remember that number, 14,400. So what is the significance of this? Well, firstly, we've shown mathematically that we're given a proof, you could say a mathematical proof, that the best shape to get the maximum area is a square as opposed to a rectangle. So we've done that. We sort of felt that instinctively at the beginning, but we've actually done it. We've given a proof, and often in engineering and maths, you've got a feeling about something, but you've got to prove it. Nothing's really the case until you prove it, because there's a lot of misconceptions in life in general. So you've got to basically, as an engineer or as a scientist, you've got to give proof. So we've got proof that if you're doing a four-sided shape, then the optimum size is shape is a square as opposed to a rectangle. Now the other question there is that actually the best optimization for getting an area? Could we get a bigger area with a different shape? So we've talked about a square, but what about a triangle? What about a hexagon? Or best of all, what about a circle? What would a circle give us? Now, I'm not going to go into the triangle. It's something for you to do on your own, bit of homework for you if you want. But let's have a look at the circle. With the circle, would we get a bigger area? More relevant than that, if you think about it, why would you fence a machine off? The reason we fence a machine off is to make it safe, the area safer, to keep people further away. Now, if you've got a distance of 120, let's do a little diagram here. If you've got a fenced off area, that's very quickly and roughly draw a square. It's not quite a square, but it's 120 along here. Okay, let me draw that right on that. So we've got here 120 meters. That means that in the middle there, if somebody walks up to it, up to the fence, the closest they can get is 60 meters. Okay, 60 meters radius, put 60 in there. Okay, so that means if something flies out of the robotic arm at speed and travels 70 meters and hits you, clears the fence and hits you in the head, then you could be a dead man. So is there another shape that would give us a bigger protection, a longer radius? And obviously when I say radius, there's the clue. Let's have a look at a circle. Okay, let me just move this page up a bit. So remember that figure 14, 400 and 120. Okay, so we've got a circle. What's the equation for the area of a circle? Of, let's start with the circumference actually. The circumference of a circle, and it'll be a good idea to put the pen back on again. How many times do I forget to do that? Circumference is equal to pi d, as you'll all remember, I'm sure, or in our situation probably better to say 2 pi d. So in other words, that's 2 times pi. Let me just take a step back there, I'm missing something out. Okay, 2 pi d, and we know that our circumference is equal to 480 meters. So in other words, and I've made it, I'm making mistakes today for fun. That should be radius squared, radius, oh la la, radius. Okay, so I know that my radius, if I rearrange my formula, I'll have 480 divided by 2 pi, or simply 240 divided by pi. Cancel that down, and that will give me an answer of, looking at my notes, 76.4 meters. 76.4 meters. That means if that article had flown off that machine, it might, well, if it could have cleared the fence, it's just cleared the fence at 60 meters, then it's going to hit it at 76. Could even hit it way down. So in other words, you're not a dead man anymore, you've survived. So if you think about it, we've got our circle, that's a terrible circle. The radius is bigger, so you've got more protection. Now the other question is the area bigger? With our square, our robot had 60 meters working range there, and it had a bit longer at the diameter part. But really our radius was 60 all the way around most times. So with this we've got more working range. Alright, I accept a circle doesn't fit into a factory as easily as a square or the rectangle, because we tend to build the factories square or rectangle shapes. Okay, but that aside, we'll just ignore that little fact. would we get a bigger area? Well, let's have a look. What's the area of a circle? Well, the area is pi r squared, which gives us pi times 76.4 squared, which gives us, again, refer to my notes, 18,337.4. I bet none of you did that in your head. Square meters. So obviously a lot bigger, well, a fair size bigger than our 14,400 meters squared. So we get a bigger area with a different shape. In fact, I've not proved this, but I suspect if you try all the different shapes, sizes, then you'll find that the circle's the best optimum area. Logically, really, because you think about it, as you add more and more sides, it's going to get, the area is going to get bigger and bigger. So a hexagon is going to be better than a square. An octagon is going to be better, and so on and so forth. And when you keep increasing your number of sides, you end up with a circle eventually. And the length of the side tends to 0, you've got a circle, haven't you? Okay, so that's logical. So basically, there's a bit more background. So if you're doing, like a lot of my students are doing BTEC, level 3 BTEC, and we're covering this in the assignment for BTEC, this gives you something to discuss to get those merits and distinctions. So you can talk about these aspects about the effect the shape has, the protection, the bigger the area, if you use a circle, and so on and so forth, and gain yourself those extra marks. So there's a little tip for free, and that's what you get with listening to videos, watching videos on YouTube instead of playing on your PlayStation. So you get more points at college. So well done. And for everybody else, it just hopefully gives you a better understanding of what's going on. So thank you for listening.